Hello, welcome to Tech Talk with Balu. Today in this video we'll be deep diving into Android software update architecture and some of the evolutions that's happened within the architecture and some insights on what happens in your phone when you press that button to say, yes, let me go get my phone updated to a new version, and a bit more into where else Android is used, like automotive systems, so on and so forth. So let's dive straight in. Now let's delve into the Android software update mechanism. So there was a big challenge with Android software update, a single point of failure. The challenge, so prior to seamless updates, which we'll get to in a bit, Android used a non-AB or what we call an in-place software update model. And this required booting or rebooting into a recovery environment, making the device unusable for a period of time. So this was so because the partitions or the software had to be flashed was just a single partition. So that had to be unmounted for it to be written into. It did present another problem or critical flaw. Any interruption, aka power loss or write error during the flashing process, could very well leave your device in an unbootable state or brick state, and often requiring user-initiated recovery or a full reflash of your device. An analogy for a non-AB update would be a bridge, where you had vehicles moving from point A to point B through the bridge. Now, if the bridge were to go through a maintenance or roadwork, then you would temporarily block any traffic through it, which meant that the vehicles wouldn't be able to travel anymore. And that's where Android brought in this paradigm shift through redundancy using A-B partitions. So what this is basically an architecture where you have two slots, slot A and B, right, which are basically two full sets of those critical partitions, right? So slot A and slot B. Slot A, which is the active slot, always maintains a known good bootable OS, right? While the update, software update, is then applied always to slot B, which was inactive at all points. What that meant is you could do a background update, right? Your phone could be running at that point in time. You could be using your phone. The user wouldn't even know, whilst you could be updating and writing into that copy, which is slot B at that point in time. So no unmounting, remounting saga happening at that point. Amazing. So if you have to take the same analogy of the bridge that we looked at earlier with a non-AB update, with an AB update, it's almost like you have a redundant bridge, such that if the original bridge was undergoing maintenance and vehicles weren't able to go from point A to point B, you now have a parallel bridge that the vehicles can use whilst the bridge is being updated. Now, let's delve into the four-pillar architecture of Android. At the top, we have the orchestrator. The update engine is the orchestrator of the software update. It's a stock Android framework component that performs the software update. Next, we have the foundation, which does the partitioning. You have the slot A and slot B partitions there, and what we call super partitions and cow snapshots, which we will get to in a bit. And finally, we have the gatekeeper, which is the bootloader and the boot control HAL. Throughout all these different layers, we have the guardian, which ensures security of the new software that's been installed. Let's talk a bit more about the update engine. The update engine is a single-threaded C++ daemon that runs a low-priority background process. It orchestrates the entire update, as we said earlier. The update engine streams the payload that it receives and writes it directly to the inactive partition's row blocks. It's pretty clever. It doesn't require that payload or the new software blocks to be stored on the device before flashing into the inactive partition. Now let's look at it at one piece at a time. The first diagram there shows how the fragments of data that has been received by the update engine is then taken and then flashed to the target partitions. The next bits talk about what we call delta updates, which is another clever mechanism that is used for software update. Delta updates is a mechanism to download only the software that has been changed. So what it would do is it would use an algorithm, typically something called as BSDiff, for example, to compare those two software binary files. It then identifies which bytes have changed and then creates a patch file out of that. This is great because it gives you two significant advantages. One, you don't have to download the entire package into your device. You just often have to just download a delta image, which is not in gigs, probably something much smaller because it's only got the difference or the changes as such. This saves on the cost of download over Wi-Fi or other mechanisms onto your device. This is very, very important, particularly for automotive applications, because for automotive applications like your infotainment screens, the OEM, typically the car manufacturer, pays money from their pocket to facilitate these downloads. So delta updates save a lot of cost for them. Number two, because you are really dealing with a smaller size of package and then reconstructing that delta package as a full package on the target Typically, the install time or the flashing time would be a lot faster. Again, a very significant advantage. However, there is a limitation that comes with the traditional Delta algorithms. They work great on uncompressed data. However, for Android, the system images and the APKs are full of compressed files, like the zip files, the gzip files, or the APK files. And because of how compression works, if you change just one letter in a text file and then compress it again, the resulting compressed file looks completely different. This is, by the way, called an avalanche effect. Now, a standard Delta tool sees a totally new file and will not be able to create a small patch. And this is where Google's Puffin tool comes into play. It is specifically created by Google to solve this compressed file problem that we mentioned. What it allows Android to do is to create tiny Delta packages, even for files that are heavily compressed. What it does is it kind of reverses some of the compression to an extent to then perform a Delta update and then recompress the image. So all that is very good, and we are ready to do a software update. But how do you verify that what you've actually wanted to flash has been eventually flashed? Okay, there isn't corruption or bit flips in the images or blocks that you have transferred, because remember, it's all fragmented and you're transferring chunk by chunk and writing into a physical hardware device. So that's where the payload manifest or the metadata comes into play. Before downloading the data, the update engine fetches this manifest file. This is basically a to-do list that tells the engine exactly what to write, what to patch using Puffin or Delta algorithm, and what the final SHA-256 hash of each block should be. SHA-256 is a hashing algorithm that can be run on these blocks to get a hash that can later be compared for validation verification purposes. So after a block or set of blocks are written, the engine can read them back, hash them, and then compare these hashes against the value in the metadata to ensure that the data in that particular disk that we've written now is bit perfect. So that's great. We are able to now flash. We are able to verify what we have flashed. But one of the other questions could be, what if you have been interrupted during this process? Like, what if there was a power loss? No problem. The update engine handles this perfectly well. The engine periodically saves its progress as a checkpoint. If the connection is lost, or if the phone reboots, for that matter, the engine does not start all over again. It looks at the last successful checkpoint, and then it resumes from that specific block. So it is interrupt resistant. So far, all good. Now let's get into the next challenge. How do you ensure that what you have flashed is indeed from a trusted source, as in that software image has not been messed around or changed or tampered with? Remember, earlier we talked about the SHA-2 and the hashing. That is to make sure that your software integrity is checked, so that you know whatever you think you had and whatever you flashed is exactly the same. What we're talking about here is the actual software that you have received on your device, let's say from cloud or from a different source, has not been tampered, like man-in-the-middle attack, or is somehow a different software to what you've expected. This is where AVB comes into play. AVB stands for Android Verified Boot. It provides cryptographic assurance that the executed code is from a trusted source and has not been tampered with. The whole concept uses what we call the chain of trust, using keys, which is signed. So the root of trust key, the public key, is stored in a tamper-evident hardware. And the bootloader then uses this particular key to verify the signature of the top-level VB meta partition. The VB meta partition is special because that metadata file contains cryptographic hashes and signatures for all the other boot critical partitions. So by just verifying that the VB meta partition file is intact and verifying the signature of the VB meta partition, you ensure that the rest of the system or rest of the software has not changed or has not been tampered with. Another key point I want to bring in here is what is called as the anti-rollback protection that Android provides. Basically, what it does is it prevents your software to be downgraded into an older, vulnerable version of the software. So let's say, for instance, you had found a bug in your software or one of the libraries that you've used, and then you've kind of fixed that by upgrading your software to a higher level. Then what would typically be done is to mark that older software version as a vulnerable version, so that you would never want to accept a software update to go back into that old version, because that exposes the vulnerability. That's typically done by an index counter, which is incremented. So two things here. One is verifying that the software is not tampered with. And number two, you don't want to receive a software that is not tampered. So that's signed, that's properly been sent to us, but somehow happens to be an older version of the software that somehow had got a vulnerability in it that could then be exploited. So Android blocks that. Here on the left is the depiction of authenticity checking with AVB, where the hardware root trust, then the bootloader uses and verifies the VB meta signature using that, which then eventually verifies the boot partition hashes. And then BBmeta provides the system partitions root hash to kernel for dmverity checks. On the right side, you see how dmverity then is able to do some sort of runtime integrity test on the software. So what it uses is something called as a Merkle tree, which is a hash tree, where the root hash is signed and stored in BBmeta. So each 4K data block of your software then is hashed, and those hashes are recursively hashed up to the root. Now, when a block is read from the disk, dmverity, what it does is it calculates its hash and verifies it against the tree. This is far more efficient than verifying the entire partition at boot. And now, what happens if dmverity detects a corruption? If it does detect a corruption, then the device reboots immediately. On an A/B system, typically this can trigger a rollback, or of course do several reattempts or retries. Eventually, if the system is not fully verified, then the system would remain partially usable for data recovery and displays a red warning screen. We'll get to that in a bit later. So next, we're going to talk about the bootloader logic and the boot control HAL. So the bootloader, or the boot control HAL, maintains a set of flags for each slot. That's what they do, basically. But basic things like whether that slot is successfully booting, whether it's unbootable, what the retry count is, so on and so forth, is maintained by the boot control HAL. So the typical flow, as you can see on the right, the scenario is that we're trying to boot slot B. Is the slot successfully booting? Yes, carry on booting slot B. If not, then retry and decrement the count in terms of attempts to boot slot B. After the counter has expired, then basically the boot control HAL would mark slot B in this case as unbootable. So it kind of maintains that state and flags for the boot process lower down. So in essence, to look at this one, boot control HAL is kind of the standardized interface between the OS of Android and the device-specific bootloader. And then it kind of maintains a set of flags for each slots, which then determine the boot sequence. So the boot control HAL is also able to kind of control the boot slot, active boot slot, as seen over here, which is typically stored in the MISC partition, which is one of the partitions where that particular flags are stored. But kind of look at it as a low-level bootloader functionality that's the cornerstone of the A/B resilience that Android provides, and thereby allowing autonomous retry and fallback logic. Everything is kind of mostly enabled using this boot control HAL. So stitching all of that together, so after the software update happens or is complete, where the new software image is written into the inactive slot, the user is then prompted with a screen to say, yep, you've got to restart your phone to finish your update. Remember that restart is not to do the complete update, because that update is complete. It's just to swap that slot to the new slot. In this case, in this example here, we are in slot A, which is the active slot. And what we're trying to do with this restart is to move into slot B. So bootloader powers on. It reads through the boot control HAL, through the MISC partition that it's got the flag saved there. It's going to read that the active boot is now slot B. So swap your slots. So don't boot slot A, boot slot B, and basically do all of those validation, etc. on slot B. Now, this period of where the new software is booting, that is slot B, is not really a successful software update yet, right? This is typically in a software update world referred to as activation or post-activation. So you've activated the new software, and now you've got to verify and do a couple of tests before you kind of finally conclude that the software update is complete. So this is kind of the trial boot period, and that's what the bootloader of Android kind of considers it. So now, once we are booted up and we are in this trial boot period, an update verify, which is a small daemon that runs early in the boot process, that kicks in to perform a final integrity check. Basically, to avoid reading the entire multi-gig system file partition, the update verifier just reads a specific list of critical blocks that is defined in a core map file. And this file is generated at build time and lists the blocks that are essential for the core system stability of Android. Now, if the update verifier successfully reads all the blocks in the core map file without any dmverity errors, we know the SHA-256 that we've talked about earlier, all of that passes, everything is okay, we're seeing a perfectly working system. That is when it kind of uses the boot control HAL to mark the successful flag. Now, the bootloader then permanently commits to the new slot by clearing the retry count at that point. This is kind of a stage which we reach to where we say your trial period is complete, we have tested everything, and we are committing the software. That is usually then the end of the software update, where now we have slot B. Every single time that you boot your software or your phone, slot B is what is then kind of marked as your active slot by the boot control HAL. That's where your software would boot from. Slot A then is your inact bank at that point. So now we're coming into another evolution that's happened in Android to solve a different problem that we will get to in a bit. Something called as the super partition. So if you look at things how it was before on Android, you would have a partition which was a physical, rigid partition. It's inflexible. The partition sizes meant that it had to be a particular size that was then allocated in a partition table. If you had a software that would basically grow in size, you could fit to the size of that partition, but any lesser, the partition would still occupy that space, right? So eventually you have a level of rigidity in your system and no flexibility. And what the super partition did was kind of gave you this dynamic resizing ability with a partition. And what that meant is you had one super partition, which then virtually you were able to kind of divide or resize into multiple partitions within that super partition and dynamically reposition and resize based on your growing software image, right? So everything becomes very flexible and dynamic. So essentially it acts as a container for logical dynamic partition. So system, vendor, product, all of that becomes dynamic and replaces the rigid partition table for OS partitions, and allowing them to be created, resided, or deleted during an OT update. You could just dynamically do what you wanted with that particular layout. Now, this layout itself is defined by a metadata file that is stored within the super partition itself. For an AB device, there are 2 copies of the metadata, one for each slot. That is very important to know that you have these 2 meta files. So while super partition gives you that dynamic, flexible way of repartitioning on the fly during a software update process, we do have another evolution that we want to talk about here that is really a game changer on Android. So remember when we talked about AB storage, we were talking about duplicate partitions. For all the partitions that we wanted in slot A, we create and replicate another redundant set of that partition so that we could update in the background. Now, often it becomes a problem, especially when you're talking about automotive applications and ECUs. Space comes with a price. So what we demand there is 2 times the system space because of the redundant AB kind of partition. The way Android came out with this interesting mechanism of snapshot enabled in a way to live with just one version or one copy of the partitions. So think of your cow file as an instruction manual for the update. Basically, it can contain 4 types of data. One is like, you could say replace, brand new data blocks, please. You could say copy, don't change anything, move the existing data to a new location, or maybe third option would be 0, just clear a block, so instructions to clear block. And yet you do have another option where you could just do an XOR operation, which is storing very tiny differences. So basically, the cow file just gives you some configuration to say, you have your old software there in your partition, where you don't have a different partition now, right? We are talking about just one single partition. But to go to B, I have this cow file. Please apply the cow file because the cow file has got all the changes you will need in a very compressed, efficient file. Read me and apply that particular file to get to slot B, as in to get to the new software. So all this raw data inside the cow file is typically compressed using LZ compression or similar to keep the file size minimal. And the next question you may ask is, who creates these cow files and who manages these cow files, and how does that all get applied back to complete your software update? So basically the difference is calculated during the build process outside of software update, right? By the manufacturer using OTA tools, so on and so forth to create the manifest. Remember the manifest that we talked about earlier. On the device, the update engine then reads the manifest. It coordinates with a component called lib snapshot to write the necessary data that's required into the cow file while the user is still using the phone. So basically, rather than writing and streaming into that secondary partition, which does not exist now, remember, you just have one super. And like I said before, the cow files is stored within the super partition. And if that's full, it kind of then spills over to the data partition or user storage partition as a temporary hidden file. Now, you see what the snap user daemon does, the one that we talked about earlier. That's kind of the traffic controller, right? When the phone reboots into the update, the OS thinks that it is reading from a complete new system. In reality, though, the snap user daemon intercepts those requests. If a block hasn't changed, then it points the OS to the base partition. If a block has changed, it pulls the new data from the cow device and so on and so forth. So that's kind of how the snap user daemon manages booting. And the final result? This kind of gives you the element of seamless update experience with nearly instant booting while significantly having reduced the storage size or mechanism using the old dual pan partition. Once that is all signaled correctly, then you go on to what we call the merge process, where the actual cow files are then taken and then merged into the super image, the physical partition, which then is called a commit of your software. It's a successful software update. Let's quickly talk about some of the verified boot states and color codes that Android provide. If you did see an yellow screen when you boot up your Android, that just indicates that you are loading with a custom OS or rooted phone, perhaps. If you did have an orange screen, that just means the bootloader is unlocked. That just means that, again, from a security point of view, you are compromising. Software integrity cannot be checked because that is provided by the bootloader, which you've modified. If you did see a red screen on boot, that is a bad news, because that just means that DMVerity has said, look, we found a corruption. We are not able to verify the authenticity of your software, which is not now trusted. Hence, I wouldn't boot it. Well, it just means that you'll have to go into recovery and do a couple of recovery stuff at that point. So where are we? Let us summarize everything that we've talked about in this video. We did say that you have your software update packages that come in as stream. The Android update engine basically orchestrates the update. It never saves, it streams the software update packages as chunks. You do have the AB seamless update, but we talked about the virtual AB snapshot or cow files that it creates. The next time when the user does get a prompt to say you need to reboot your phone, basically Android takes the cow files and applies that to the super base partition, the physical partition, and boots the new software image, which then goes through AVB to do some verification, authentication. The update verifier checks the software is all good. Once that is all signaled correctly, then you go on to what we call the merge process, where the actual cow files are then taken and then merged into the super image, the physical partition, which then is called a commit of your software. It's a successful software update. Should AVB and the software update process detect that the new software isn't right or is not for some reason good to proceed, then we kind of activate the rollback process, which just means that merging wouldn't happen, the cow files get deleted, Android would boot back into the super original old software image. That's, my friends, a quick overview of Android software update architecture. Do let me know if I've missed anything, or would you like to hear a bit more about any particular area in the software update process, or generally from a software architecture point of view. But if you did enjoy this video and learn something new, please do leave a thumbs up and consider to subscribe for more such videos. Thank you very much, and see you guys soon.